Question 24 shows us a couple of circuits with resistors in series and in parallel, and asks us to work out the ratio of the current in one circuit to the current in the other circuit. So to do this, let's take one circuit at a time. So circuit 24.1, let's call it, for the first one. We can work out the combined resistance here. R total is equal to R plus 2R, because these are resistors in series, so therefore the resistance is simply 3R. So the current using V equals IR, the total R, we can work out the current in the circuit is V divided by 3R. And let's not worry what V is for now, because that will be cancelled out later. For 24.2, we have two resistors in parallel, so we have to use the resistors in parallel equation, which is that 1 divided by RT, the total, is equal to 1 over R plus 1 over 2R. In order to simplify this, we need to multiply top and bottom of this first resistor by 2, so that would give us 2 divided by 2R plus 1 over 2R, which can be simplified to 3 over 2R. And finally, if we invert both sides, we'll find that R total is equal to 2R divided by 3. This means that our current, I, is equal to the voltage divided by 2R over 3, which gives us 3V over 2R. So now to find the ratio between these two currents. So we begin with our first current, 24.1, which is V divided by 3R divided by 3V divided by 2R. And if we now manipulate that equation, we get V times 2R divided by 3V times 3R. The V's cancel, the R's cancel, and that leaves us with 2 divided by 9, which is equal to 0.22. Part B gives us an experiment that students conducting with two identical filament lamps and a variable power supply that has no internal resistance. The lamps are connected in series, the current is 0.03 amps, and the lamps are dimly lit. The student then doubles the EMF, and he expects the current to double, but he finds that the current actually only increases to 0.04 amps. The lamps are now brightly lit. Use your knowledge of physics to explain these observations. Well, the first thing we should recall is that filament lamps are non-ohmic. They do not have a constant resistance. This is because as the voltage increases, the current increases, so the temperature increases. Which increases the resistance. V equals IR, so an increased resistance will lead to a lower current. Part C gives us a circuit connected by a researcher who's trying to determine the resistivity of a metal designed from waste metals. we're given the length, cross-sectional area of the wire, and the current and voltage readings for the wire as well. We're asked to determine the resistivity of the metal. So your formula sheet will show you that resistance R is equal to the resistivity rho multiplied by the length L divided by the area A. We need to rearrange that equation to give us the resistivity is equal to the resistance multiplied by the area divided by the length. So the resistance we don't know yet, so we need to use V equals IR, or R equals V over I. The voltage is 1.8. The current is 0.026, giving us a resistance of 69.2 ohms. So we can feed that into our calculation here. 69.2. They've rather kindly given us the area rather than expecting us to calculate the area from a diameter. 1.3 times 10 to the power of minus 7 square meters. And the length of the wire is 0.75 meters. Now this gives us a resistivity of 1.20 times 10 to the minus 5 ohm meters. And part II explains that this is larger than the value the researcher predicted. So we should explain one possible limitation of the experiment. Well, one limitation is that the current in the wire caused a heating effect, thus increasing the resistance and therefore the resistivity of the wire. There are other things you could say here. One consideration is the crocodile clips that the wire is connected to. We don't know what the resistance of those are. We don't know also that the crocodile clips were connected with 0.75 meters of wire between them. They could have been connected not exactly at the ends. So both of those limitations would also be valid. Thank you for watching this video from Cowen Physics. If you found it useful, please like, subscribe, and visit cowenphysics.com.